Hey guys, welcome back to my channel. Today I'm going to talk about two sample test hypothesis when two samples are related to each other or dependent of each other. One of the students asked me to talk about that topic because he or she's going to take an exam this Friday. So that's why I made this video in a little bit of hurry and hopefully it can be released, before your exam. In the video later, you will see that I just use one example to make the video short and concise in order to be released before your exam. I just use one example to show you the whole process of doing this hypothesis testing for two related samples. I think that is the most straightforward or intuitive way to understand the process. I hope you'll find it helpful. And by the way, to fully understand everything that I said in the video, you should have some background knowledge of one sample test hypothesis. Okay, because this is for two sample and two related sample. Okay, so without further ado, let's get into the video. Let's work on a two sample test hypothesis when two samples are dependent or related to each other. Okay, so now I have the population contains this many observations. 1, 2, 3, 4, all the way to n. This is my population. And then I ask this many students to take the test and collect the test score. Called X test score before. This B stands for before. I have X1, X2, X3, X4, all the way to X sub n. And then ask the same amount of students take the test and after some intervention. So there could be a test prep course or training sections to train the same amount of students. Before the training, ask the student take the test, you collect test score, and after the training section, you ask the students take the test again, you collect the test score after, right? So X1, X2, X3, X4, before and after Xn. So you have n students. You see, this is for B, right? This is for B. And this is for A. You know this, right? So different variables before and after, right? This arrow stands for some intervention. So you see, these two values, right, are related because it's for the same student's test score. This one type of dependent populations, the two populations are dependent because you see this is one measurement, you have test score, one measurement, an intervention of some type, and then another measurement. And then these two populations are related, or you can understand it as a pairing or matching or pairing of the observations. So these two values are a pair, right? Or because this is a pair of scores for the same student, a pair of scores for student number 2, right? The two values are paired or are matched, right? Because it's for the same observation or same student. So you can consider this as a population 1 contains this many observations, and this is a population 2 contains the same amount of observations. Or you can think of this as paired observation, or the other, one type of dependent samples measurement, intervention of some type, another measurement, and the other type of dependent samples or dependent populations are matching or pairing of the observations. So that could be the example of before and after study, or the example of matching or pairing observations. Okay, so two populations. Out of this population, you randomly select, suppose 8 students. So 1, 2, 3, 4, 5, 6, 7, 8. You get their test score before this intervention. For example, 90, 80, 60, 75, 85, 92, 88, 79. And after this intervention, you collect the test score. That's after. Right? From this population, you select same number of students in the sample. The same student number 1 before 90, after, for example, 100. Student number 2, before this training, you get 80, and after 93, 60, 82, 75, 81, 85, 92, 100, 94, 87. So now you look at these two we call it two samples. These two samples coming from the two populations because populations are related and the two samples are related, or 90 and 100, these two values are paired or matched or related because it's for the same student. So your hypothesis is this: H null, maybe mu1 equals mu2. Okay. Alternative one, mu1 not equals mu2. Depends on your research question. Maybe this is our research question, or maybe your research question is whether mu2 greater than mu1. Right? And mu2 not greater than mu1. So whether this training section helped to improve the student test score. You want to compare the two population means, mu1, mu2, through comparing two sample means, x1, x2. Right? So how to do the test with two dependent samples? Let me write here. It's x1, x2. What we do is you convert two samples, right, two dependent samples into one sample, because it doesn't make sense to compare 90 with 82 because that's for a different student. It does not make sense to compare student number 4's test score before the intervention and student number 5 test score after the intervention, right? It only makes sense to compare before and after, right? The score before and after for the same student. So what we do is we find the difference between before and after. Just use after minus before, right? You have this 10, 13, 22, right? 6, 7, 8, 6, 8. So now you convert the two dependent samples into one sample. So this one particular sample contains this many observations. And you can compute the sample mean. We just use d bar to indicate sample mean, right? Sum d divided by 8, right? So 10 plus 13 plus 22 plus 6 plus 7 plus 8 plus 6 plus 8 divided by 8. You can calculate that equals 10. You should know that this average of differences, your average of this 8 differences exactly equal to, because you use after minus before, exactly equal to x bar 2 minus x bar 1. That's your average. Get average score after minus average score before. If you're confused with this, let me show you very quick here why these are equal. Suppose this x1, x2, x3. This sample contains y1, y2, y3, and the average will be y bar, average x bar. And then you find that you convert this into one sample. So y1 minus x1, y2 minus x2, y3 minus x3. This one sample. You get this average. Right, this is a difference 1, difference 2, difference 3, the average of all differences. What I want to show you is d bar equals exactly y bar minus x bar. Right, d bar exactly equals y bar minus x bar, right, after minus before. So it equals y1 minus x1 plus y2 minus x2 plus y3 minus x3. 3 observations divided by 3. You look at what you got. y1 plus y2 plus y3 minus x1 plus x2 plus x3, and then divided by 3. That exactly equal to y bar minus x bar. So that means this average of differences equals the difference between two averages. So now you already convert two dependent samples into one sample, and this is your hypothesis. So if, let's suppose this is our hypothesis. So if there's no difference between two population means, that suggests no difference between two sample means. Okay, now we know this one population, take a sample, another population, take a sample, and this is our new sample contains 8 differences. So an important question to ask is, the important thing to know is, if this is one sample, what is the corresponding population? The population should be You get all the differences, XA after minus XB, right, before. You have all the differences. So I can add another column D, right, D1, D2, D3, D4, all the way to Dn. So this is the corresponding population. This is a population. Out of this population contains this number of differences. You randomly choose a sample of it. So you just focus on this population and this sample. Okay, so now you can actually rewrite this alternative and null hypothesis. Let me rewrite this. i.e., null hypothesis, the population mean. The population mean, let me just use d bar. The population mean is 0 because there's no difference, right? The difference, average of difference is 0, meaning mu2 minus mu1 equals 0. Right? So d bar equals 0. Alternative one is d bar not equal 0. And if we use a 5% significance level, there's only 8 observations, so t-test, right? So we have this. Sample, out of this population, you choose a sample. You have the sample mean, right? So sample mean should follow normal distribution. With the population mean, hypothesized population mean 0. Okay, and you see t-statistic. So in order to use the central limit theorem, you need to assume this population follows normal or nearly normal distribution. Okay, all the differences should follow normal distribution or nearly normal distribution in order to use t-statistic. Okay, so 5% two-tail. So that's maybe 2.5% here, 2.5% here, and you can find the critical values. This is a t-test, right? It's not 1.96 because it depends on degrees of freedom. So degrees of freedom, this is our sample. It contains 8 observations. So degrees of freedom should be positive way to think about it. A minus 1, 7, right? So now degrees of freedom equals 7. And 5% two-tail, degrees of freedom 7. You can easily use a calculator or Excel or any other software or even table to calculate, to find the critical value, dividing point. So let me show you the table because it's easier for me to find and to show you. So degrees of freedom 7. So look at this row. And 5% significance level, 5% two-tail. So now this is the critical value, 2.365. 2.365. Okay, that means this is 2.365, 2.365. Okay, and now you have the sample mean is 10, so you should convert 10 into t and compare it to 2.365, right? So t value for d bar, right? The value of d bar minus average of d bar divided by standard deviation of d bar. So that's 10 minus 0 divided by standard deviation of d bar. That standard deviation, the sample standard deviation, right? Sample standard deviation equals sum each value of d minus average squared divided by degrees of freedom. Take a square root. You can solve for it. But this is a central limit theorem, actually. So you should, don't forget to divide it by square root of n. So, central limit theorem. X bar follows normal distribution with the mean population mean and standard error of this distribution. Standard error equals sample standard deviation divided by square root of n. So you can solve for this whole thing, right? This whole thing. Standard error equals 1.90. So 10 over 1.90, you can solve for it. That equals 5.26. So 5.26 is way greater than 2.365, right? So it's here. So we reject null. That means if there's no difference between two population means, it's very, very unlikely that you have the sample mean this large. And then if this is your hypothesis, you just use one-tail test. So d bar and average 0. So this is 5%. If you use default 5%, so you can solve for critical value. And then 5.26, whether this 5.26 is more extreme than the critical value. Right? 5% one tail, degrees of freedom 7. So solve for critical value. is extreme than that. So you reject null hypothesis and accept the alternative. Okay, so that's two dependent sample test hypothesis. Yeah, hope you find it helpful. Hope you found today's video helpful. Any questions, comments, please let me know. I really appreciate all the questions and comments. Thank you so much, and give me ideas and inspirations about what videos might interest you. Yeah, thank you so much for watching, and stay tuned. See you next time. Bye.